Section 2.2 Work. When an object is pushed by a constant force, work is equal to that constant force times the distance this object travels. What if force changes as the object travels? Well, we'll have to resort to calculus. If the object has traveled dx distance, and between x and x plus dx, approximately the force is constant. Therefore, we can compute the amount of work. It's F times dx when this object travels from x to x plus dx. Again, because the distance this object travels is infinitesimal, approximately we say the force is constant. And what if the object travels a finite distance? Well, we'll put integral sign in front of f dx. We'll simply just sum up all those tiny dx. And then the integral of f dx is the amount of work. Now let's talk about the compression or expansion of a gas. So in this picture, a force is exerted on a piston. The piston is pushing the gas. So how do we compute the work? It's simply F times dx. And remember, F is equal to pressure times the area. Therefore, we replace F with P external times the area A. And over here, this is the equation for expansion or compression work. And because dV, the change of volume, is A times dx, the change of distance, we can see this clearly here. The volume of this white space is dV. It's dx times the surface area over here of the piston. And therefore, we have the equation W is equal to negative integral of px dV. So two things. One, we need a negative sign here. Why? Because when the volume decreases, this dV is negative. However, in that situation, work is done to the system. So work should be positive when dV is negative. So that's why we put a negative sign here. Two, we need to pay attention to this. This is P external, not the pressure of the system. Why is that? Just imagine this scenario. What if a system expands against vacuum? How much work can this system done to the vacuum? There's no way for anything to do any work to a vacuum. Therefore, the result should be zero. Work is zero when a system expands against vacuum. And therefore, this equation is going to provide the accurate answer. P external is zero, it's a vacuum, and then work is zero. About the signs. When a system expands, work is negative. Over here, this without a subscript is referring to the work of the system. When the system is compressed, work is positive. Again, in this situation, work is done to the system. The internal energy of the system increases. So work is transitory. Why is that? Because if you look at the equation for work over here, we need to know how this P external changes during the expansion or compression process. So work is not really associated with the state of the system. Given the initial state of the system and the final state of the system, there is no way to evaluate the amount of work. So mathematically, if you're given the lower limit and upper limit of this integral, you cannot compute the work unless you know how this P external changes with volume. So this P external can be a function of volume. You need to know what the function is. If P external is a constant, you need to know what's the value of that constant. And then you can compute work. Now let me give you an example problem. So let's calculate the work for two different processes, A and B. And then we're going to compare the result. So you will see in the end, given the same initial state and final state in A and in B, the results are going to be different because the two processes are different. First, process A. A 20-liter ideal gas with a pressure of 4 bars expands to 80 liters against external pressure 1 bar. So I forgot to put another condition here, which is assume this is an isothermal process. Therefore, you can easily compute the temperature given the number of moles. However, we don't need that information honestly. So work is equal to negative P external dV. And then we put in this external is 1 bar constant. And we integrate this dV. And volume changes from 80 liters to how many liters? Well, it's an isothermal process. So the product of PV remains constant. Why? PV equals nRT. Temperature is constant. So PV is constant. The initial PV is 80 bar liters. Therefore, the final PV is also 80 bar liters. So it confirms. Now it's going to be from 20 liters to 80 liters. So the amount of work is negative 60 bar liters. Pay attention to the negative sign. That means the system does work to its surroundings. The system loses energy by doing work to its surroundings. Now let's change the process. We're going to do a two-step expansion. First step, this gas, same initial state, 20 liters, 4 bars. We're going to allow this to expand to 40 liters against partial pressure, against external pressure of 2 bars. Again, it's a constant temperature condition, isothermal condition. And then the second step, it's going to expand to 80 liters against a different constant external pressure, which is 1 bar. So there are 2 steps. We'll have to calculate the work for each step. And then we're going to sum it up. Step 1 over here. Remember, this P external is a constant. It's 2 bars. The volume changes from 20 liters to 40 liters. So you do the integral. Well, it's negative 40 bar liters for step 1. Step 2, similar calculations. What's the change? The external pressure now is 1 bar. The volume change is from 40 liters to 80 liters. What's the result? It's negative 40 bar liters for step 2. So in step 1, the system does 40 bar liters of work to the surroundings. Therefore, it's negative. Step 2, again, the system does work to its surroundings. We sum it up. Overall, in this 2-step process, the system does 80 bar liters of work to its surroundings. Therefore, we put a negative sign here. Again, when the system does work to its surroundings, the internal energy of the system decreases, assuming Q is 0. All right, assuming Q is 0. But sometimes Q is not 0. Actually, in this example, you will see later, if it's isothermal expansion of an ideal gas, W is negative 80 bar liters, then Q is positive 80 bar liters. All right, you'll see that in section 3. So now let's compare the 1-step process and the 2-step process. So in the 1-step process, the system does 60 bar liters to the surroundings. In the second 2-step process, work is negative 80. So they're different. Again, work does depend on the process. To compute the work, you need to know what the process is like. Is that a 1-step or 2-step? What's the value of P external? And if P external is a function of volume, what's the form of that function? So finally, a third process, C. Again, the same initial state, the same final state, but this time I want to say P external is equal to P in the entire isothermal process. So this P external is not going to be a constant because this pressure of the system changes with volume. So still, we start from the definition of work, negative integral P external dV, and then we can replace this P external, this external pressure, with the system pressure because of this information. And then this is isothermal process, remember? So PV equals nRT, so pressure is nRT over V. This time, we're not integrating a constant. We are integrating a function of volume. So how do we do that? Remember, the integral of dV over V is ln V, the logarithm of V. So this is the result. And then we plug in the numbers, we'll get the amount of work. However, we don't know what the temperature is. Fortunately, we don't need to know what the temperature is because temperature is a constant. So nRT is simply PV. At the beginning, in the end, during the process. So we're going to use the available information. We know the initial pressure and the initial volume. and we can compute this nRT. nRT is PIVI, it's 80 bar liters. So we replace this nRT with 80 bar liters, and we calculate this LN4, which is roughly 1.4, I believe. The logarithm is natural logarithm. I think the base is 2.71828. Okay, LN4 is roughly 1.4. You do the math, it's going to be negative 111 bar liters. It's different from negative 80 bar liters in process B. It's different from process A, which is negative 60 bar liters. Now, in reality, if P external is equal to P, the system cannot expand because the inside and outside pressures are the same. How can the system expand? But just imagine, if P is slightly greater than P external, for example, they differ by this much. See how small this is. And then there's a pressure difference. The inside pressure is greater, therefore the system can expand. But at the same time, we can say P is equal to P external because look, this 10 to the power of negative a billion Pascal is negligible. So we can assume this P is equal to P external when we do this numerical calculation. So again, this equal sign holds.